I'm sure it was Charlie who requested this video. So, hey Charlie, I hope this is useful to you and to anyone else who's watching it. The topic is Redshift. Before I explain what Redshift is, I want to check you know about spectrograms. Light from the sun can be split into the visible spectrum using a prism. This is a spectrogram of our sun. You can see there are dark lines. These are called absorption lines or spectral lines. These spectral lines help us to work out which elements there are in the sun, because particular elements absorb particular wavelengths of light. So we can look at light from our sun and from other stars in this way. We use a spectrometer to produce a spectrogram, and all of that will be important in a minute. So, on to Redshift. Oh, no, hang on a minute. There's another thing I need to check you know too. It may seem odd when Redshift is to do with light from stars, but let's just think about sound for a second. Have you ever heard of the Doppler Effect? I remember Millie telling me this was her favourite episode of The Big Bang Theory, so this picture's for you, Millie, as we talk about the Doppler Effect. Sound waves with different frequencies or wavelengths have different pitches. High sounds come from high frequencies or short wavelength vibrations, and low sounds come from long wavelength, low frequency vibrations. Listen to the police car as it comes towards us and then moves away again. As it drives away, did you notice what happened to the pitch? It gets lower. Meow. So, what must have happened to the wavelength? That's right, it got longer. The wave got stretched because the frequency got lower. There were less waves per second. As objects move away from us, waves are stretched. This increases the wavelength as the frequency decreases. Now we're totally ready for Redshift. Let's compare the spectrogram of our nearest star, the Sun, here, with the spectrogram of a star that's further away from us. That's this one here. Both stars are made up of the same elements, so we see the same spectral lines, but they have shifted over to the red end of the spectrum in this star that's further away from us than the Sun. Light is a wave. Different colours of light have different wavelengths and frequencies. Red light has the longest wavelength and the lowest frequency of all the colours. If light waves are stretched, the wavelength gets longer and the frequency gets lower. So if the light is moving away from us, the waves are stretched and the object appears red. Or if we look at the spectrogram, the absorption lines shift towards the red end of the spectrum. The two theories about the origin of the universe, the Big Bang and the steady state theories, both use evidence of redshift to support the idea that the universe is expanding. The idea that galaxies are moving away from us. Galaxies that are further away from us are moving faster as well. This can be seen because the more distant galaxies show a greater redshift. The light is stretched even more, so the wavelength decreases even more and it gets even lower in frequency. So the absorption lines shift even further towards the red end of the spectrum. So that's Redshift. I have only one more video request on my list now, which is velocity time graphs. So that will be the next video that I make. Watch out for a notification that that's ready. But if you have a topic, don't forget to leave a comment and request a future revision video, because you know that
Regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.